mentioned a really good point there, and that is the thermal lag that happens in our building.
Hey, now I know what it's called.
Thermal lag.
Thermal lag.
This is the one and only, the original podcast where you can find yours and your business's true value. You're listening to Our Value.
Brought to you by America's insulation source, IDI Distributors.
You want to hear from the best contractors, suppliers, and consultants that dedicate themselves to more than just survival in the business world?
Industry professionals that are dedicated to excellence in every aspect of their business.
Our Value has them all here to share that same motivation and knowledge with you. Tune in and grow a more successful, profitable, educated, and recognized business. Listen to the Our Value podcast to become the industry leader in your market. Find your value with Our Value.
Well, Our Value podcast listeners, we have a treat for you today. I have Mr. Allison Bailes. That's Dr. Allison Bailes. Is that correct?
I have a PhD in physics.
Well, I have Dr. Allison Bailes on today, and actually, he started out more as a physics teacher, but then started building a house, and then 20 years ago got into what he's into today. And if you don't know Energy Vanguard, you should. You should be going to the Energy Vanguard website and blog and read what Allison puts out. He loves to write. He claims he does that more than video, but really starting in 2008, you're going to find a lot of articles. You mentioned that your most popular one you've ever written was the 4 pitfalls of spray foam. Is that the case, Allison?
That is absolutely true, and it has been the winner every year. For the annual traffic each year, it has come out number one every year except for 1 year in 2020. I got more traffic on my IAQ articles because the pandemic got started, and I wrote a lot about filtration and ventilation, and those articles got tons of traffic. So the 4 pitfalls dropped to number 4 that year.
Wow. So pitfalls aren't as important when people are really concerned about IAQ, evidently.
Yep.
Well, speaking of that, IAQ it's a tough beast to tame, especially when we have intersecting trades on projects. And one of the first things I wanted to talk to you about was right sizing of equipment. Over the years, I've been in foam a long time. And over the years, what I've found is you can really get between a rock and a hard place with some contractors on the sizing of their equipment when we're making buildings as tight as we are. And you put something out that I've shown almost every class, and I get eye rolls, I get all kinds of things, but mostly bewilderment. You said at one point, we're even doing some buildings today that we could put at 3,000 square feet per ton. How do you look at right sizing? What's your main things that you look for on that, or if you're having the conversation with a mechanical contractor? By the way, guys, Allison is known as the premier designer of HVAC systems in the United States. I've heard that. I didn't hear that come out of his mouth, but I've heard it come from several others. And so that's why the question here. So how do you go after that and initiate the conversation? But really, what's the metric you're looking for? Are you just using RightSoft?
Number one, we start with a load calculation. We don't use rules of thumb. We use an actual load calculation where we enter all the data as correctly as we can. So we get it, all the specifications for the house, whether it's a new house or an existing house. We do lots of design for new construction, but we do some renovations. Usually, when they're full renovations, gut rehab. But we've got to have the full specifications because we want it to be as accurate as possible. We want to know, what the R values are in all the walls, ceilings, floors, what the window specs are, what air tightness they're going for, think they're going to hit or have to hit for a certain code or program. And all that goes into the software. We do the load calculation, and we know that there's some leeway there. We use you mentioned RightSoft. We use the program RightSuite Universal from RightSoft, the company, and it if you do everything absolutely correctly in entering it, you're still going to end up with some excess load most of the time. The the loads that you calculate that way, the heating and cooling loads, will be a little bit higher, 10 to 15% higher than you really need. And so then we do our equipment selection based on Manual S, and we get the equipment information, look at the expanded performance data, or the software, the proprietary software with some equipment. Like we do a lot of Mitsubishi systems, and they've got their software called Diamond System Builder. So we use that to get what the capacities are going to be for the different kinds of equipment and different configurations, match that up with the loads, make sure that the equipment can meet the loads, and then clients come back to us later when they talk to the contractor. If our client's not the contractor, then they come back to us and say, "Oh, the contractor said this will never work."
That's the point I wanted to get to.
Yes, we've had that conversation a million times.
And how do you address that conversation? Because I've been there when we first landed Meritage Homes. We were talking thousands of houses, and they said, "Great, come out and do the model homes." The contractor refused to put in systems. All of our loads said that we should be 1,150 square feet per ton. And the contractor refused to do it. And so, we went back and forth, and there was all kinds of, mud on the floor or whatever you want to call it. And we did do it right, but we're sitting there in the model home on the day of grand opening, and it's 105 outside and 200 people through the model home. And CR looks at me and goes, "My gosh, we're still oversized. How does that happen?" And I told him, I said, the best that I can come up with is in Europe, they account for convective bypass or convective looping in walls and things like that, where our softwares don't account for that. I said, "I'm sure we're just doing great," because it was with the door opening all the time, it was still 74 inside. So how do you address that conversation?
Well, what I told you, we talked to him about the load calculation and how we have done this hundreds or thousands of times, and we have a good feel for the tolerance of the load calculation. We've done equipment that we've commissioned. I've got equipment in my house that we did full design for. We did the load calculation and all the duct design and everything for it, and it works fine. Actually, the equipment in my house is undersized. We don't do this for clients. In my house, the equipment is undersized, and that works fine. And that's what I was telling you. The load calculation still gives you some oversizing. When you put in the numbers for the load calculation, you put in design temperatures. The design temperatures are we use the 99% ASHRAE design temperature, which means that only 1% of the hours in a year will the summer temperature, the high temperature, be higher than the summer design temperature, and only 1% of the hours of the year will the outdoor temperature be lower than the winter design temperature. Now that's averaged over decades. So sometimes you will have more hours than that in a particular year below the winter design or above the summer design temperature. But the design temperatures that we use are temperatures that homes don't see very often. So, in Atlanta, our design temperatures for summer is 92 degrees. We get up to 92 degrees pretty much every summer, and we get above 92 degrees sometimes. But we start off in the morning around 70 degrees, sometimes in the 60s, and then it climbs during the day, and it gets into the 90s in the afternoon, and then it starts falling again at night. So there's three kinds of temperature, three kinds of loads to pay attention to. One is the design load, which is what we get from the load calculation. But the equipment is almost never operating at the design load, almost always operating under part load conditions, because our summer design temperature is 92, but we're almost 99% of the time, we're less than 92 degrees in the summertime here. And then you've got extreme load, which is like, I don't know what the design temperature was for the house you were talking about, but if it's 105 degrees outside and your design temperature is 99, you're 6 degrees above your design temperature. So that would be an extreme load. So you're beyond the load calculation. But remember that you're not 105 degrees 24 hours a day.
One of the things I think that we don't account for is, okay, So Dallas, it's 101, we'll say. Well, that doesn't mean that 101 has made it through the building materials to the interior wall where the change and the load and everything gets addressed. So maybe that doesn't happen until 6. Well, by 6:30, it's already cooling back down. So I think there's still this carryover kind of thing that we don't account for. I'm undersized as well. And I think in the South, it's a great thing to be undersized just because of trying to deal with the latent load and hoping that my equipment struggles a little bit just so that it runs long enough to take some water out.
You mentioned a really good point there that I hadn't gotten to yet, and that is the thermal lag that happens in a building.
Now I know what it's called.
Thermal lag.
Thermal lag.
The outdoor temperature hits 105, let's say 4 o'clock. But I've got data on runtime for my air conditioner. Well, the previous place I used to live, and the high temperature had happened like 4 o'clock, 4:30 maybe, and my highest runtime is going to be 2-3 hours later, like 6, 7 o'clock. That's when I'm getting my highest runtime, because that's, we put insulation in the walls, we have air sealing, and that slows down the heat transfer. So the heat gain from outdoors in summertime is slower because of the thermal properties of the building enclosure.
I know that we need to get these guys on this, but today we're even seeing low load buildings and low load calculators now for HVAC. In new construction, do you think that we're going to continue to keep lowering loads, or are we going to, do you think maybe balance off by adding fresh air where our loads are kind of about where they're going to be, but we're going to bring in more air? What are your thoughts on that?
The code is working on lowering the loads more. I mean, the air tightness requirements have continued to change for the better. And so, then there's also, the difference between the model codes like the IECC and the ICC, IRC, and the adopted codes. Like in Georgia, if we followed the model code, the IRC and the IECC, we would be at 3 ACH 50, but the task force that put together the code changed it, and it's 5 ACH 50, not 3. So, there's that improvement that can happen too. So there's a code lag. In addition to the thermal lag in building, there's the code lag. So that, and we're on the 2015 IECC in Georgia. Eventually we'll go to maybe the 2021, and maybe we'll get to 3 ACH 50. So the requirements are still improving there, and things like having continuous insulation on the outside instead of just cavity insulation, and having greater R value requirements. In Georgia, we are still R13 walls. We don't have any requirements for continuous insulation on the outside or 2x6 walls. So it's just 2x4 R13 right now. But that I hope will change.
My point was, we'll tighten the building, but then as we continue to add fresh air requirements, we're actually going back to increasing the load. And so how we address that, the dehumidifiers and things like that, which we'll get to that in a minute, but you talked about air tightness. What do you think are the biggest things missed when tightening a home from your experience and what you've seen over the years?
Air tightness actually is an area that we've improved a lot on, because there's a blower door test, and you either pass it or fail it. If your state says you got to meet 5 ACH 50 or 3 ACH 50, there's a number you have to hit. Now, some people cheat, and they put down a number that they didn't hit just to satisfy the inspector, who's not going to check and not enforce it properly. But there's the blower door test and the threshold that you have to hit has made air sealing a lot better. In terms of places where builders have trouble, one is, anytime you have places where you have joists. A good one is, an attached garage, and you've got a wall between the attached garage and the living space, and you've got joists ceiling joists running above that wall. You need to have blocking and sealing in between those joists above that wall, because there's going to be places where air in the garage can get into that ceiling area and move into the house, and through the interstitial spaces, fancy word for the all the building cavities and everything, and so it can go into a hole in the garage wall and go across that open space between the joists over the wall to the house, and then come out through a switch or a receptacle. Cabinets, the soffits above cabinets often, have been a problem because they are left unsealed. Another place where joists are a problem is if you have attic knee walls with unconditioned attic space on one side and conditioned space on another, like a bonus room and other places upstairs. The joists running under that knee wall also need that blocking and sealing, because air can get right under there. And even if that air can't get into the place, it can heat up the floor or cool down the floor. Yeah, lots of places. I mean, the little things people are pretty good at. The fire blocking has helped with that. The penetrations through the top plates for wiring and things like that. We've been sealing those since before we had to do blower door tests.
Yes, and that's a good thing. So when you look at these moisture loads in foamed buildings, I loved it when Dr. Joe first came out and said, "Hey, wet air rises." I'm like, yeah, it does. So when we look at these, especially in the South, we have all these foamed attics, and we've seen the moisture load go up in there and really, add a lot to it. When you think of that and you think of the manual LLH and how we're making these tight buildings, are you seeing that in any of the ones that you get involved in?
Yes. Oh, yeah. And I've written about that issue a number of times, high humidity and spray foam attics. And in the Southeast, where the spray foam is almost always open cell spray foam, which is vapor permeable, that humidity, the water vapor in the attic air at nighttime can go right through the foam and hang out in the roof sheathing. And what happens is that it really collects up near the ridge. And if it stays wet enough, long enough, that, that part of the sheathing can rot out. You mentioned Dr. Joe and his work on this, and he came out with what he calls the vapor diffusion port. So one thing you can do is you can still have spray foam, but you put about a foot and a half or so down from the ridge. Instead of putting rigid sheathing there, OSB or plywood, you cover that with a vapor permeable material that is air impermeable. So house wrap would be a good example.
Yeah, Tyvek on there.
Any of those kind of materials that will stop air movement but allow vapor to move through. So it has to be vapor permeable. Then the humidity that goes up can then go out through the top, because, as you said, the humid air rises, and the up near the high part of the attic is where the humidity is, and I've got measurements on that. It's it's dramatic, the difference in the humidity level, when you look at the data logger at the floor of the attic versus at the ridge of the attic.
How big of a swing are you seeing? 20%?
So number one, the dew point and the relative humidity cycle, they go through the diurnal cycle. So every day, as it cools off at night and heats up during the day, the humidity level, the dew point and relative humidity cycle up and down. In the afternoon, on a hot summer afternoon, the humidity and the relative humidity and the dew point are way up there, especially at the ridge. And at nighttime, the humidity goes down, even the dew point, not just the relative humidity, but the dew point goes down, which is an indication that water vapor is going through the foam and hanging out in the roof decking.
Yeah, so it's making its way out of the building.
Well, it goes in,
not out of the building, into the products, into the building products.
Yeah. If there's a vapor diffusion port, it can go out of the building.
Right. Now, they're also wanting, the 2018 code wanted either you open the mechanical in the attic or you pull wet air out of the attic, encouraging dry air to come up from down below. inside the structure. But the real thing is it has to be addressed. We're seeing a lot of issues there. And so with all of this, we just start looking at the air tightness and all of the things. Insulators aren't out there running manual J's. I know you can show them load calculations, but is there really anyone out there training them or helping the mechanical contractor to, quote, get it or to understand the dynamics of these newer buildings that we're building?
Yes, they're I do that with the Energy Vanguard blog and speaking and training and other stuff that I do. There are other people as well. There's some really good people in the mechanical industry who are doing a great job with this. Brian Orr, if you haven't heard that name,
yes,
he's amazing.
Brian is awesome, and he's out there preaching the right things every day.
He is. I mean, he's got his daily podcast, and his audience, he's aiming at HVAC techs, the guys who are in the trucks going out to fix air conditioners every day and furnaces and install stuff. Those are the guys he's aiming at, which is great because this is the kind of stuff they need to hear. I mean, and I get his daily email in my inbox. I think the one that came yesterday was about the psychrometric chart and humidity. So,
if you could create the perfect insulation contractor, the one that you would hire, what would they always do? Insulation
and the air barrier, I think, go together. So number one, they would understand the building enclosure and the importance of maintaining the integrity of the building enclosure. Any hole that gets punched, anybody who punches a hole needs to own that hole. So in terms of insulation contractors, though, the installation is the key thing with insulation. I mean, all kinds of insulation materials can work, and all kinds of insulation materials can be installed poorly. I've seen foam board installed poorly. I've seen spray foam installed poorly. I've seen fiberglass and cellulose and everything. I mean, any kind of insulation that you can think of, it can be installed poorly, and that they understand the properties of the different kinds of insulation.
So now on ventilation, because we've hit on ventilation a couple of times or, kind of talked around it. What is your favorite kind of ventilation for a residential structure?
It depends on where you're talking about. Somebody in Florida or Houston or, any very high humidity coastal climate, ventilating dehumidifier.
Love that.
Would be great. And sometimes if people have the budget, some of our clients have the budget and they know they need a dehumidifier for those climates. So they want that, but they also want an ERV. So they do the dehumidifier is not a ventilating dehumidifier, but just a supplemental dehumidifier for the indoor air. And then they bring in outdoor air through the energy recovery ventilator, which has recovery. So it's not bringing in as much moisture as it would be. So there's less to dehumidify once it gets in. And it also exchanges heat. So the air comes in pre-cooled in the summertime, preheated in the wintertime a little bit because of that energy exchange that happens. So, and, for the general locations that, not the high humidity place, an ERV almost everywhere, occasionally HRV, and that's mostly Pacific Northwest.
But Minnesota, Ohio, ERVs are fine?
ERV, yeah, because, in cold climate like Minnesota, you want an ERV because with an HRV, you're going to dry out the indoor air too much in wintertime because your humid air in the wintertime is inside the house. Outside air is very, very dry. You bring it in and warm it up, and now your humidity goes down close to zero. So you want that moisture exchange in Minnesota too for wintertime to keep the air from drying out too much.
So what do you think of vented crawl spaces?
Vented crawl spaces can work in dry climates. They can work. You have to do something with the floor above them to make sure they're airtight and insulated properly, and that's always a difficulty. In humid climates, and anywhere in the Southeast, vented crawl space is a stupid idea. because you're bringing in lots of humid air, and you've got water pipes and ducts and things that can get condensation on them. You start growing mold, and they're nasty places.
Yeah, I've found, so many lake houses. You could be in Nebraska with a lake house, and a vented crawl space is just a terrible idea, because you're just creating a biological growth environment. You could call it a cell enhancement device or something. It's I really struggle with them. One thing I've been starting to see, though, with this air tightness movement that we've got, and granted, a lot of the homes I've been involved with were around one air change. A lot of the others, Matt Reisinger and I did one that before spray foam, it was at 0.87. So, it's not, foam isn't the boss of air sealing anymore. It's a great, tremendous product, but we can air seal buildings now and have them below 3 ACH simply by getting things right. And so I look at that, and my question for you is, should everywhere in the U.S. have an optional dehumidifier for their property when you're building tight?
Not everywhere in the U.S. And dry climates don't need a dehumidifier. I wouldn't.
Yeah, not Phoenix or Vegas.
Well, actually, Phoenix sometimes might.
The monsoons.
Because they have their monsoon season, and they do have higher humidity there. And but in a lot of places, you don't need a dehumidifier. Out west. Basically, a lot of out west places. People think that when they think of Seattle, they think of rain and wet and damp. But Seattle actually is a dry climate in summertime, and in wintertime it's cold air is dry air. So when the temperature is 40 degrees outside, that air comes inside, it's not humid. So one thing you can do whenever you have cold or cool air outside is you can dehumidify by bringing outdoor air in.
With our contractors who really, want to get some help with mechanical design, should they reach out through your website, go on, start getting the Energy Vanguard blog?
Yeah, I have a weekly newsletter. I send it out every Tuesday, and that will have links to any new articles that I've written since the previous newsletter. I put a weekly column in there. I have links to other stuff like conferences that I'm speaking at and things like that. Also, a little update about the book that I'm writing, which is very close to being sent to the publisher now, and will be out this summer. It's called A House Needs to Breathe. Or does it? Because you and I both know a house does not need to breathe, but a lot of people think that a house needs to breathe, which is just absolutely not true.
One of my favorite pictures of all time is Larry Zarker with the breathing mask connected to the dirty wall, asking people if they want to take a big old breath out of their wall or would they rather have fresh air. I absolutely love that. Well, Allison, thank you so much for your time today, for being on the podcast, and just in general for helping out the industry.
Oh, you're very welcome. It's my pleasure.
Thanks so much for listening. If you've got any HVAC design questions or got a consumer that it's going to go south and things aren't going to go well, I would seriously reach out to Energy Vanguard, get them involved in the design of the HVAC system, and make sure that your customers are doing the right thing. We look forward to hearing from you in between now and then, but then come listen to our next podcast.